as I've been on this journey with Flink since quite some time, actually since 2016 when I joined Data Artisans, the original creators of Apache Flink. And back then I was developing inside Flink, mostly on the network stack. You can probably still see some slides on the net on this. Then I eventually switched gears to support customers, to do troubleshooting, to do trainings and other things as a solution architect. And eventually Data Artisans was acquired by Alibaba and renamed to Viverica. Later on, I joined the crew at Immerok to build a fully managed Flink cloud service. And that one got acquired by Confluent. And this is why I'm here now. All right, now Flink. What is Flink? Apache Flink is a framework that connects, enriches, and processes data from almost any source in real time. The data can be used to create rich real-time use cases and has had a huge impact on many traditional industries such as banking and retail, and also enabled new business models like ride-sharing platforms. And it's no wonder that by now Flink has been adopted by quite a few companies that use stream processing for their innovative products like Uber, Netflix, Stripe, and others. So what are the use cases? Well, digital natives use Flink and also naturally combined with Kafka to create rich real-time experiences for their end users to differentiate them from the competition, such as the ones you see here. Like Uber is using it for real-time pricing. Netflix has been quite an early adopter of Flink, uses it for personalized recommendations, and there are a lot of fraud detection use cases out there in the world. You can broadly categorize those stream processing applications into three groups. There are streaming data pipelines, which move data from point A to point B, doing some processing along the way. There are also aggregations for real-time analytics, such as usage metering and billing. And there is a whole group of event-driven applications, such as fraud detection or anomaly detection, geofencing, and others, which often involve using a rule engine or a pattern matching library, or extracting features for machine learning models. Let's dive a bit into Flink's architecture and see how it is running a job. Flink applications, as I mentioned before, are consuming data from one or more event sources. Those sources can be files, it can be messaging systems, it can be databases, or any other service or application that produces data. Then after processing, Flink is writing those results into one or more sinks. But how do we actually write a Flink application? For that, Flink offers a couple of APIs in different languages. If you broadly categorize them by the level of abstraction, you end up with a picture like this. It starts with process functions at the lowest level, then there's a data stream API in Java, then there's a table API, which is also in Java or Python, and then there's Flink SQL. Internally, however, these APIs are not built on top of one another. So internally, it looks something like this. There's an even lower level stream processor, a stream operator API, that each of the other APIs can use and leverage and optimize upon to have access to low-level primitives. Table and SQL API are more or less the same thing conceptually. They present their data differently, or the program is done a bit differently, but in the end, they will run through an optimizer, which will then leverage the low-level APIs, whereas data stream API and process functions are sitting directly on top. Let's now have a look at a Flink SQL query and how this translates into a Flink application. So I want to start very high level. This is why it shows SQL, and we'll see more of SQL throughout the talk. All right, so we're reading data from sources. That's what I said earlier. So we define a source here. We're reading from a table. In that case, we want to enrich that data in the table and amend it with windowing information. We want to group the items that are in this table by windows of 1 day length in this example. We tell it what the timestamp is to use for that grouping and what the other table is to read from. In that case, the transactions table could be a Kafka topic, but it actually depends on what you define this table as. It could also be files. I mean, let's assume for now it's a Kafka topic as a natural source for streaming data. Then this creates, inside Flink, it creates an operator that is reading from the source. And well, we also need to amend it with the windowing information. Now we want to select a few things, and we want to group this. We want to calculate the daily revenue for each item in this transactions table. So we group things by the item, because we want a daily revenue per item, and then also per day. So we group it by the window, in that case, the window end timestamp. And that ends up in another operator that is calculating this daily revenue, and it's doing aggregations by a certain key, in that case, the item and the window. Eventually, we want to write this data out. We don't just want to keep it to ourselves inside Flink. We want to write it to a new table or a new topic in Kafka to make it available to other users or actual applications for dashboards or whatever this is being used for. So we write this into a sink, in that case, a topic in Kafka, our revenue topic sink, our revenue topic. Now we have the job, but we want to run it. For that, you need to know that Flink is running in a separate cluster. That cluster consists of a job manager and a set of task managers. Each of those task managers provides some task slots to actually run an instance of your job. When the job manager is now receiving your job from a client, like either you submitting it from the console, or some automation, or you have a different deployment model where you start this inside Kubernetes, this is being submitted to the job manager. It is then responsible for creating or getting the resources that are needed to run your job. Either the task managers are already there, or it needs to get them and create them. Once the job is running, the job manager still remains responsible for maintaining the life cycle of this job. It is crucial for, well, first of all, starting it, eventually also stopping it, but in the meantime also for fault tolerance. We'll have a look at the details a bit later. It coordinates this fault tolerance, checkpointing, and eventually the task managers are running your job, and you can give a result back. The task managers are actually the only things that are running your job. This is where the actual data is being read from the sources and also written to the sink. The job manager is just orchestration. Now, let's dive into Flink's core streaming concepts. Its performance and robustness are the result of 4 core design principles. It's streaming as opposed to batch. It's a shared nothing architecture with local state. It's event time processing, and it's state snapshots. And we'll look at each of these 4 topics in a bit and how they fit together. We'll start with streaming. Whether it's orders or shipments or downloads or clicks, business events can always be streamed. These streams of events can be manipulated, can be processed, and can be reacted to in real time. In which case, the sequence of events form an unbounded stream. And that one extends indefinitely into the future. Event streams can also be stored for later retrieval and for reprocessing. If you reprocess a batch of historic data, it's basically, at least for Flink, just a special case of streaming. In that case, the stream has a starting timestamp and it has an ending timestamp. But otherwise, you start the stream to read from somewhere and you read indefinitely into the future. So for Flink, everything is a stream. This is the job from earlier. I only split it into parallel instances and colored those parallel instances so that you know the yellow one is run on one of those task slots on a task manager, the blue one on another one, and the purple one on the third one. Stream processing is done in parallel, otherwise it wouldn't scale. This is done by partitioning the event streams into parallel substreams. Each of which can be processed independently. I mean, you're used to this. Like in Kafka, you have your topics that have partitions. Those are your parallel input streams, basically. You just need to group them to your parallelism that you run this job at. It's a key point for scalability of Flink and other stream processors. The independent parallel operators share nothing. They can run at full speed individually. Like if a particular partition is read on the yellow operator, then it's not read by the blue one. It's typically the case that the input into a Flink job can be consumed in parallel. Like for Kafka, that's the case. Either those sources are partitioned already upstream, or you can do that later, or you can do that later. And we'll have a look at some of those like connection patterns in just a bit. Because at each state of the job graph, your application code will use one of Flink's APIs to define A, what the job or what this part of the operation is doing, and B, how it should send the results, or where it should send the results to and how. In this example, the first operator is collecting input from the source, what we read from Kafka, and then we forward it downstream. Forwarding an event is the simplest thing an operator can do. It's also very cheap because Flink will optimize it quite a bit, and therefore it's handled efficiently. It's just a local handover. Think of one function calling the other in a Java program. The second operator is just adding windowing information. And then it's reorganizing the stream for the third one, because we wanted to group the events that we received by item. We wanted to do aggregations by item. Since the individual parallel instances share nothing in between, we have to send items that are related or that the individual operators need. So we send all the orange ones to the first operator, all the blue ones to the second, and others. Sometimes a shuffle or repartitioning like this is necessary for relocating items. And it brings together, well, all events for a particular item so that can be processed by the same node. Only that way we can aggregate data from all these events that belong together. Shuffling, on the other hand, is more expensive than simply forwarding it. We have to, well, each event has to be serialized, and we also have to, depending on where it's being sent, we have to send it over the network. Whereas the forward was just a local operation, this is now sending data over the network to a different task manager. The third operator now has the results of a revenue calculation for daily revenues. And now it's being forwarded to the sink. Instead of keeping the same parallelism for this example and forwarding the events as earlier, I've chosen to instead change the parallelism. In that case, we only have one sink. So we have the output of 3 operations, and we need to send it to just one sink. This is called a rebalance, and in Flink, it's just a round-robin fashion-style operation. So that all the different results that are produced by the third operator are merged at the sink and then available at our topic that we want to write to. The decision to rebalance in this particular example, well, first of all, it's an expensive operation, same as the repartitioning we've done earlier. It might send data over network, probably will. So therefore, events need to be serialized, also need to be sent over. It's more expensive. So typically, you probably don't want to do this as I did here, where it's just one sink. You would just have 3 of them as the operator before, and then it would just be forwarded, and it would be faster. But this was just to showcase the different connection patterns. Actually, Flink has a few more. There's, like, in addition to forwarding, repartitioning, and rebalancing, Flink offers other patterns like broadcasting streams to a set of operators, or joining streams together in a single one. But I'll not dive into those for the sake of time. Now let's turn our attention to the topic of state. Flink is a stateful stream processor. So what does it mean to be one? First off, not every operation has to be stateful. Like, we had the second operator, which is just amending data with windowing information, and that can be done with data from this event itself, like only from the event that we're processing. In that case, we have the timestamp, and then we put this into a daily bucket. So we don't need anything else. We don't need to store anything, and therefore, this is a stateless operation. Other operations could be filters, where filter out certain events based on a property, or maps, like, well, this is technically also a map where I enrich something. I could also remove fields and other things. Like, all those are stateless operations. Now, the more interesting part is counting and other aggregations, because they need state. Because we calculate the daily revenue for any given item type, one parallel instance of the counting operator will see all of the events for that item type. This is why we needed the repartitioning. Flink manages this kind of state in a distributed key value store. With each parallel instance, okay, it's one of the, or each of the three, managing the state of some of the keys, like only those that were routed into that operator instance. Because of this, state is local to each operator, and if things are local, you don't need to share anything. This is fast. Now there's also an additional form, let's say special form of state, that is associated with the operators themselves. Sources, for example, read from Kafka topics. They need to know where they read from, so like the current offset. Things, on the other hand, might also need to store information about the events that have sent out already, so that in case of failure, they don't have to send it again. This type of state is usually small, as it is not tied to every particular event. So this operator state is, let's say, the smaller of the states. The typical one is the state I was talking about earlier. That is the big part you will see in Flink. Now, before we get to fault tolerance, let's look at time a bit more, because time is a crucial component in stream processors. Flink distinguishes between event time and processing time. Processing time is sometimes also called the work log time, and event time is the time where an event was originally created or being recorded or produced. Like at some point, an event got a timestamp. This is the event time. While processing time is the time later on when you see that event, when you process it. Imagine like I flew in here on Saturday, for example, but if my stream processor is just seeing it now, this is the processing time now, and event time is when I flew in, when my flight was. Event time is generally preferred for calculations, since this is consistent. Whether you process something or do an aggregation now, or whether you did it in real time, it will always produce the same deterministic results. Processing time, on the other hand, can be simpler to work with, and therefore is sometimes chosen as well. There's a trade-off between the two. Timer generally is used to synchronize streams, to connect them in a meaningful way, or to wait for something to happen, like a window to end. With event time, events or event streams might be perfectly in order, but they're usually not. Events travel at different speeds, there are delays. For example, like in this scenario where there's a mobile application, the event that was created at 10:14 could be arriving earlier than the one that was created at 10:10. So we need to take care of those out-of-order events. So let's look at a stream of events and their timestamps. We start reading from right to left. We see the rightmost event first. This is at 1:50, and then we see event C at 1:56, and so on. If you look closely, you'll see that these events are somewhat out of order. For example, there's an event at 1:55, and that is processed after the event at 1:56. Processing out-of-order events like this one can be challenging. Imagine you have a window. You want to calculate aggregates over an hour. So the window started at 1 o'clock, and you want every data for the time between 1 o'clock and 2 o'clock. You're reading the event stream one by one. At some point, you need to decide whether the window is done, whether it was 2 o'clock or not. But how are you able to decide? When you read this event at 2 o'clock, for example, you don't really know yet whether there will be any out-of-order events coming up after. In that case, there is one. But we only know this because we see the global picture now. If you process it in real time, you don't have that. So we need to implement some heuristic so that we can use that for the windows and determine whether a window is probably complete and that there are no further events before the 2 o'clock timestamp. or that they're not likely to exist at least. What this decision boils down to is an assumption of how out of order a stream actually is. And Flink's watermarks are the concept that Flink uses watermarks for exactly this. They are based on assumptions on the degree of the out of orderness of a stream. In this example, we made an assumption that this source has data that is out of order for at most 5 minutes. When you tell that to Flink, it creates a watermark. A watermark is a special kind of event that carries a timestamp. The watermark flows with your normal records, and the timestamp is simply computed by subtracting the out of orderness estimate, in that case 5 minutes, from the largest timestamp you've seen so far. Each watermark tells us something about the completeness of the stream with respect to time. Specifically, the watermark is an assertion that the stream is now complete up to, but not including, in that case, 145 timestamp, and that there are no earlier events expected after that. Earlier events are still possible, but that was not our assumption. We didn't expect this to happen. But there's nothing preventing from the whole pipeline to see earlier events. How you consider or how you handle those earlier events then is basically up to you. You could drop them or you can process them separately. Like they are called late events. When we started the discussion about the watermarks, we had this question of when should the window operator continue? So when does it know that the 2 o'clock timestamp has passed? We can now answer that question. It's the window should continue whenever it sees a watermark of at or beyond 2 o'clock. Then we know it's complete, at least complete to our assumption that we defined for that source. Great. So this is event time. We move on to fault tolerance and snapshots. We talked about state. I mentioned state as local. Now, if state is local, but you're in a distributed process like this, like Flink is running things on multiple task managers, then what happens if one of those task managers dies? Like your local state will be gone as well. Flink needs to somehow quickly resume processing and do that without making mistakes. Well, what kinds of mistakes are we worried about? Well, Flink could, for example, fail to produce some of the expected results. Or you might produce duplicates. Both are things we want to avoid. In another situation, you might want to pause the job. Maybe you have a bug in your application. You want to pause it for a bit, fix it, redeploy. You also need some state there in order to continue where you left off, because usually you don't want to restart from the very start that you read data from. So for this, Flink has 2 types of snapshots. One kind of snapshot is a checkpoint. Checkpoints are automatically managed by Flink and are taken for the purpose of recovering from failure. They are written in a format that is optimized for quick recovery. On the other hand, there are save points. There's a different kind of snapshot. They are written in a format that is optimized for operational flexibility. They're not created by Flink, they're created by you. You manage the lifecycle of those snapshots. To sum this up, checkpoints and save points there are 2 different kinds of snapshots. Both can be used to recover from, but in different scenarios. Regardless of which type of snapshot it is, all snapshots are written to a durable distributed file system. Well, they should be at least. They could be written to S3, for example. To make this fault-tolerant and also give us processing guarantees, Flink implements a variant of the Cheney-Lamport distributed snapshot algorithm, which produces globally consistent snapshots. This is coordinated by the checkpoint coordinator that is run on the job manager. In this example, each of the parallel sources has written into the snapshot, like at the very start, checkpoint coordinator sends a starting signal, and this is traveling through the whole pipeline in Flink. At first, the sources write the topics and the offsets that they read from. Then it adds a checkpoint barrier that is traveling through along with your data. Whenever it hits an operator, it will store its state. The second operator didn't have any state, so we can continue. It's moving on. Now we reach the point where we had our keyed state. So each operator writes its state into S3 in that example. And we can continue until we reach the sinks. The sinks write transaction IDs because we want to use exactly once guarantees and therefore not produce events multiple times. And then we need to know which event we've already sent out. So we have our state snapshot at the bottom. Eventually, when all of the tasks have reported that they have completed their checkpoint, they're part of the snapshot, the checkpoint coordinator sends a final complete checkpoint message. And this is for those operations that need to handle things in, in a two-phase commit way, so that we eventually have a complete checkpoint and we need to commit things. Like we're using Kafka transactions, for example. We filled them with data that we wrote, and in the end, we have to commit it. Now we have a full snapshot. Can be a checkpoint, can be a save point. While this is done by a checkpoint coordinator, this algorithm is used by both. Checkpoint and save point just have a different format. All right. Snapshots do not stop the world. They are being created asynchronously, so you don't have to fear them. It's not like if you take a save point that the job is pausing for however long it takes to create that checkpoint or save point. Things are done asynchronously. While the job is continuously processing events, you do your global consistent snapshot. Snapshots are global and self-consistent. Therefore, Flink provides effectively exactly once guarantees. Now, I said effectively exactly once. It doesn't mean that an event is only processed exactly once. In the event of a failure, you might have processed something already. Now you have a failure. You're resuming from the last checkpoint that you did, from the last global snapshot that you had, and you're reading that same event again. What I mean with effectively exactly once is that the result is only visible once, because it's only visible once the checkpoint has completed, as if the failure never occurred. Any failure results in recovery, and that one involves restarting the entire job, and restarts from the most recent checkpoint. If you restart from anything else but the most recent one, you will see a duplicate, because you've already committed this out. When you restart, each of the parallel instances of your job are basically reading the same state that were left from the previous run that failed, or when you stopped it manually and then resumed. All right, let's have a look at a few differences to other streaming frameworks. Well, most of the streaming concepts are shared between the common streaming frameworks. There are, however, details that differ. Here I want to focus on the difference between Flink and K-Streams, but they're similar also for others. Flink, for example, as you now know, is a standalone stream processing engine, and that one is deployed independently from your application that is using the data. K-Streams, on the other hand, is a library that is running as part of your application. So for Flink, you're running your application inside a Flink cluster that you somehow need to deploy and take care of. And K-Streams, you are responsible for deploying your application, and the K-Streams application, or part of it, is working alongside that. It also scales exactly the same, whilst in Flink those things can be independent. Flink has a custom network stack for data exchange between the individual pipelines. Like after reading from the source, whenever something is sent towards the next stage, it enters a custom network stack that is based on netty. Flink also relies on state snapshots that are written to a distributed file system. On the other hand, K-Streams relies on Kafka. It uses Kafka topics for buffering data between those pipeline stages. And it also relies on changelog topics for stateful operations to make them fault-tolerant and rescalable. So Well, as a Kafka Streams application, a K-Streams application, can be rescaled without a restart. A Flink job cannot. Like a Flink job, you really have to restart and go back in time to where you left off. On the other hand, Flink has better performance and scales better, especially with complex topologies. Because data in between the pipelines is not persisted anywhere. It's just sent over from one to the other. Flink connects to a couple of external systems directly, including Kafka, distributed file systems, JDBC, and a lot more. There are a lot of connectors in the world for Flink. For K-Streams, K-Streams relies on Kafka Connect. This also allows you to get data from other systems, but it first has to get into Kafka. It's more detail. In the end, you can use the data as you like, but yeah. All right. So much for the theory. I'd actually want to take you on a short demo. Hopefully the demo gods are with me. And I can showcase a little Flink project. So get you exposed to a little bit of it. From all of the available APIs, I want to start simple, just like in the slides. I'm choosing Flink SQL. So we'll have a small SQL project. Now, let's see, come on. There, great. My talk was too long, apparently. Come on. Oh. And I was locked out. I want to showcase this little demo in Confluent Cloud, but you can use anything. You can also start things up locally. But the main reason why I chose this is because I have sample data around as well, so I don't have to worry about getting sample data in. Okay, I want stream processing. I prepared a little bit in this. There we go. So when you start a SQL workspace, you'll find your catalog. Can you see it? Yeah. You find a catalog on the left with a couple of examples. I want to do something similar to what we talked about in the presentation. So I want to aggregate revenue on transactions. So among the sample data, we have products, we have orders. Those are tables for Flink, and for Kafka, those are topics. With individual fields, fields. So let's have a look at the orders table. Like a select anything from the orders table, and I also want to have a look at the timestamp in there. So this is why I use this system field that is called row time. All right. Once you run this query, we're basically reading data, in that case from the examples, which is not a Kafka topic, but it's a generated thing. And we're seeing the data coming along. We have our current timestamp, we have order IDs, and then can relate them to customer IDs, products, and prices. So I want to calculate, as I mentioned, I want to calculate daily revenue. I could do it from this alone, but then I would only know the product ID. Well, it would be better to see that by name, at least if I want to read it. If a machine is only reading it, that would be enough, maybe. Now, we have this product ID, but we also have a product table. So let's have a look at the product table as well. Same query, select everything plus timestamp from products. Oops. Oh, by the way, is that big enough, or should I increase the font? Can you read it? I see. A little bigger? Okay, let me try. And come on. Okay, that's enough. I can reduce this a bit. I think it gets to a point where otherwise we can't see the results anymore. Okay. So now we see the product IDs and we can correlate them with the names. Great. Now we just need to join those two things together. And, oops, I don't want to scroll through the items. I want to join. This is unfortunately not that big. I'm going to make it a bit smaller so that we can see. Sorry for that. So I want to join the orders table that we've seen earlier with a product ID in there, together with a products table based on the product ID. So we have this little thing here. This particular join is a temporal join. It's very important for streaming, because if you do not add a time constraint to the join of two tables, Flink would retain state for both tables indefinitely. Now we know that whenever we're walking through the orders table, we want to join it, or let me run it in the meanwhile, we want to join it with data from the products table at the same time when the order was created. Because when the order was created for a certain product, it must have existed before. And once I run this query, I will see, same our timestamps, and we'll have the orders table that is enriched with the product name. I call it item name here because I wanted to get close to what I used in the presentation earlier. So we have the price, which is in the amount. We have the product ID, which is now called item, and we have item name so that we can calculate our daily averages. Now, sometimes, like if I do this exploratory search or research into my data, I just want to show things in the UI as this one. But oftentimes, after you've did this research, after you explored your data set, you want to bake this into a real application. And real application, you don't want to show it on your screen, but you want to produce the data into a topic that is then read from somewhere else or shown in a dashboard. So in that case, I created I will create a new Kafka topic out of the data that I have seen. I've joined those things together, saw that on the screen, and now I want to write them to a Kafka topic. In that case, a simple create table will create the topic in the first place, and I can define properties for that topic if I want to, and it will then also fill it with the data that is coming out of my query. And this particular first part is our watermarking strategy. This is how we deal with out-of-order events. So this is how you define it inside SQL. You say, create a watermark for the timestamp column. And this is defined as the current timestamp minus, in that case, 5 seconds. So here I assume an out-of-orderness of maximum of 5 seconds. That's it. Now we have defined a watermark for our source. And the table, the Kafka topic is being filled by this statement. We can have a look at this running thing. It's running in Flink. It produces data, and I think the metrics are a bit behind. If I leave it running for a bit, we will see that it produces data. It's reading from both orders table as well as the products table, and then creating a new event in this transactions. Let's look at this. Let's have a look back later. Great. Now we can actually run our final query, the one that we have in the presentation. I want a tumbling window on the transactions. Well, I will not calculate this for a daily revenue for this example, because then we would have to wait a day to get results, because I'm just producing them now. They won't have timestamps from yesterday. So I do this by the minute and aggregate the total revenue by minute by item. Run. Oops. It's starting to run. And we should see results. There we go. We have data in our table. We see the results here. Now we have our daily revenues for each of the minutes. Great. Demo got nice with us. Now let's wrap up. Whoops, almost closed it. I'll have screenshots on the slides so you can look at it later. Now, just to wrap things up, 5 things you need to know to get started. We ran through a couple of points. I basically wanted to make those 5 as the important ones. First of all, everything is a stream. And streaming is a natural order of things. Then Flink's architecture, I'm not repeat it here, but the most important part, Flink is run on a cluster. Flink streaming applications are running on that cluster. That consists of job manager and task managers. State in Flink is local. It's fast, and it's fault-tolerant. For event time, you have to work with watermarks. Watermarks define the out-of-orderness, and they make things happen when the time is right. And as a fifth point, state snapshots are being used for recovery. They are checkpoints for being fault-tolerant, and they're safe points for you to start and stop an application, or other way around, to stop an application and resume from it. Or you can also do A/B testing. You can use the same save point and run it with different options of your job to see how things go. If you want to explore a bit more, you can have a look at developer at Confluent.io. Their colleague of mine, David Anderson, and his team have created a great set of training courses on Flink SQL. There's also content of Kafka, of course. Then you can also look at the Flink page for blogs and documentation. It's also quite helpful. And if you want to explore, like we did here, to explore Flink in Confluent Cloud, try this example out, or anything else, then you can have a look at the docs at Confluent. All right, thanks a lot.